To make the titanium inside a dental implant, a smartwatch, or your phone, humanity has to cook stubborn black ore in poisonous chlorine gas, lock it inside vacuum chambers, throw molten magnesium at it, and spend days convincing one of the most stubborn elements on Earth to cooperate. That sounds less like modern manufacturing and more like medieval torture for rocks. And somehow, this already bizarre story gets even stranger. During the Cold War, the United States secretly bought titanium from the Soviet Union to build a spy plane designed to spy in the Soviet Union. Yes, really. So, how did a metal that seemed almost impossible to make become one of the most important materials in the modern world? Let's start at the beginning. In 1791, titanium was not a metal. It was a rumor hiding inside black magnetic sand at the bottom of a stream in Cornwall, England. A country clergyman named William Gregor noticed the sand clung to a magnet like iron. Once he separated out the iron, something unidentified was left over.
This is iron, obviously. Wait, there is something else in here.
Something else? What do you mean something else?
I mean, this is not iron.
4 years later, a German chemist named Martin Heinrich Klaproth found the exact same unidentified oxide completely independently, inside a red mineral from Hungary. He had no idea Gregor had already beaten him to it, and he named the mystery element titanium, after the Titans of Greek mythology. Gregor gets the historical credit. Klaproth's name is the one that stuck. Humanity finally had a brand new element. Great news, right? Not really, because discovering an element and actually being able to use it turned out to be two very different problems, and titanium was about to spend the next century proving exactly how different. Here is the part nobody tells you. Titanium is not rare. It is the 9th most common element in the entire crust of the Earth, sitting quietly under almost everywhere you have ever walked. The problem was never supply. The problem was titanium's personality. Titanium is violently, obsessively attached to oxygen, and from the very first attempt, it refused to let go. The first idea was obvious. Do exactly what had worked for iron for thousands of years. Heat the ore, add carbon, remove the oxygen. It works beautifully for iron. Titanium had other plans.
Okay, just let go of the oxygen. No.
Instead of releasing pure metal, titanium grabbed onto the carbon instead, happily forming another completely useless compound. Scientists tried again. Titanium refused. They changed the temperature. Titanium refused. They changed the chemistry. Titanium refused. By the beginning of the 20th century, titanium had earned a reputation as the most stubborn metal nobody could actually make. It was like being rich in a currency nobody could spend. In 1910, an American chemist named Matthew Hunter finally coaxed out genuinely pure titanium using sodium instead of carbon. It worked. It also only worked in tiny, expensive batches, and for the next few decades, titanium remained exactly what chemists called it out loud, a laboratory curiosity. A metal that technically existed and that nobody had a use for.
We found a new metal! Can we use it? No! Then why are you telling me?
Then, in the 1930s, a stubborn metallurgist from Luxembourg named William Kroll decided titanium was going to matter whether the world agreed with him or not. Working largely alone, he refined a method using magnesium, and by 1938 he had produced around 20 kilograms of usable titanium, more than anyone before him. He sailed to New York to show American industry what he had built.
I have a new metal, lighter than steel, just as strong. Interesting. What is it for? Airplanes, ships, the future. We will pass for now.
Nobody wanted it. Disappointed, Kroll sailed home. Then, with a Nazi invasion looking imminent in early 1940, he fled to the United States weeks before German forces crossed the border. Great news, right? Not quite, because when Luxembourg fell, the American government assumed Kroll's own patents now legally belonged to the state as enemy property, even though Kroll was standing safely on American soil the entire time. It took him years in a lawsuit to get his own invention back. But by then, a world war had made every major government suddenly desperate for a light, heat-resistant metal, and Kroll's method became the foundation of the entire modern titanium industry. Here's what that method actually looks like, without the polite version. You take titanium dioxide, mix it with carbon, heat it to roughly 1,000 degrees Celsius, and pump in chlorine gas, essentially interrogating the rock until it agrees to give up its metal. This produces titanium tetrachloride, a liquid so allergic to ordinary air that a trace of moisture turns it into an angry, corrosive cloud on the spot. Then you bring in magnesium, which behaves less like a chemist and more like hired muscle, ripping the chlorine away from the titanium while everything sits sealed inside an oxygen-free chamber for days. Chlorine, magnesium, vacuum. Days of waiting. Finally, you open the reactor expecting a gleaming, futuristic ingot. What is inside is a crusty, ugly gray lump. The industry calls it, without any irony at all, titanium sponge. It looks less like the future of aerospace and more like something forgotten in a shower for a decade. That sponge then has to be melted all over again just to become a usable block. Honestly, at this point iron started to sound like a relaxing weekend hobby. So humanity had finally unlocked titanium. Great. Now they just needed to buy enough of it, from their biggest enemy. By the late 1950s, the Cold War had a body count and a deadline. In 1960, a Central Intelligence Agency U-2 spy plane was shot out of the sky over Soviet territory and its pilot was captured alive. Washington needed an aircraft that no missile could ever reach again, something that could fly so high and so fast that the entire concept of being shot down simply did not apply to it anymore. Working under the engineer Kelly Johnson at Lockheed's Skunk Works, the team ran straight into a wall. Push ordinary aluminum past roughly Mach 2 and the metal itself starts to soften. The new aircraft needed to cruise past Mach 3 for hours, with skin temperatures soaring past 500 degrees Fahrenheit. Steel could survive that heat. Steel was also too heavy to ever leave the ground. Only one metal could survive both: titanium. There was just one problem. America needed titanium. Titanium was in the Soviet Union. America wanted to spy on the Soviet Union. So America bought titanium from the Soviet Union to build the plane meant to spy on the Soviet Union. The Soviet Union unknowingly helped supply the material for the aircraft designed to spy on itself. History does not usually write its own jokes. When it does, apparently, it writes them in titanium. The Central Intelligence Agency built a web of shell companies and quietly went shopping in Moscow. According to stories later told around the Blackbird program, one of the cover explanations given to Soviet trade officials was that the titanium was needed for commercial pizza ovens.
Why do you need so much titanium? Pizza ovens. Very strong pizza. Extremely patriotic pizza.
The Soviet Union sold the ore anyway, eager for hard currency. Getting the metal was only half the battle. Titanium hated being manufactured almost as much as it hated giving up its oxygen in the first place. Standard cadmium-plated tools left microscopic traces on the bolts, weakening them enough to risk failure mid-flight, so everyone had to be thrown out. Parts built in summer kept failing while identical parts built in winter did not, and engineers eventually traced it to the local water supply, lightly chlorinated in warm months. Titanium hated that too, so the whole line switched to distilled water. Titanium refused again. The result was the SR-71 Blackbird, built out of titanium for most of its structure, and to this day no operational aircraft has flown faster or higher for longer. Soviet air defenses reportedly fired missile after missile at it over the years. None ever caught it. So titanium had conquered the sky. Naturally, the Soviets decided to drag it underwater too. In the 1970s, Soviet engineers unveiled a submarine later known to NATO as the Alpha class. Its hull built almost entirely from titanium, reportedly exceeding 40 knots underwater and diving beyond 1,000 feet, below the reach of most Western anti-submarine weapons of the era. Great news for the Soviet Navy, right? Not exactly, because titanium hated welding just as much underwater as in the sky. Welders had to work sealed inside chambers filled with inert argon gas, and the very first hull cracked and had to be scrapped. Even once that was fixed, the submarines were notoriously loud, easy for American sonar to detect, and staggeringly expensive to maintain. Only 7 were ever built, and the last one retired by the mid-90s. Titanium had built the fastest submarine on Earth and one of the Cold War's most expensive disappointments at the same time. So titanium survived chemistry. It survived espionage, it survived the Soviet Navy. Its weirdest opponent turned out to be a rabbit. In 1952, a Swedish anatomy professor named Per-Ingvar Brånemark was studying blood flow inside living bone and inserted a small titanium viewing chamber into a rabbit's tibia. Months later, once the study was finished, he tried to remove it.
Take it out.
I can't. Pull harder. I think the rabbit owns it now.
Titanium once again refused to let go. Brainmark named the effect osseointegration, and it should have been an overnight medical sensation. Instead, funding committees rejected him for years because conventional wisdom said the body always eventually rejects foreign material. He tested it on dogs, then on human volunteers, and in 1965, placed the first titanium dental implant in a human patient. It took until the early 1980s, after he presented more than 15 years of research at a conference in Toronto, for the medical world to finally believe him. Today, that one accident is the entire reason millions of people can get implants and prosthetic limbs that their own bodies simply refuse to reject. And perhaps the strangest part of this whole story is this. For decades, scientists have been trying to replace William Kroll's process. They've invented cleaner methods, faster methods, more energy-efficient methods. On paper, some of them look much better. So, why is the world still using a process invented in 1938? Because making titanium isn't the difficult part. Making thousands of tons with exactly the same quality every single day is. Almost perfect is fine for a toaster. Not for a jet engine, not for a spacecraft, and definitely not for something that's going inside your body. So nearly 90 years later, if William Kroll walked into a modern titanium factory, he would probably recognize almost every step. Chlorine, magnesium, vacuum, days of waiting. Almost exactly as he left it. While you've been watching this video, factories around the world have already produced tons of titanium using almost exactly the same process. It's also why titanium still costs several times more than steel, despite being the 9th most abundant element in Earth's crust. After 2 centuries, titanium still refuses to make things easy. And all that, so wealthy retirees can hit tiny white balls with titanium golf clubs.